Hello. So I'm Remi. I work for Amazon. I've been there for roughly 4 years. I'm going to talk about Kani and a style of verification that's pretty different from what we saw with Crusoe. With Kani, initially, we wanted to do something where the cost of entry is easy and it's cheap, and you just write verification harnesses like you would write unit tests, basically. Except instead of just fuzzing your code or testing it on concrete inputs, you just symbolically execute it. So I guess just to start, formal verification is very important at Amazon. We have a whole department called ARG, really dedicated to verification. And people realized initially it was an investment that cost money, but over time, verification just makes everything cheaper, more efficient. And so now there's the Amazon flywheel is also happening with verification, and Rust in particular is really growing fast inside of Amazon. So Amazon is still a Java shop for the most part, but Rust is really growing fast. So yeah, it's like formal methods started with very high level stuff like network reachability, analyzed on static, reachability policies for networks. Then it went down to like the identity and access management system, basically the upper layer of the cloud. But now that we do Rust verification and we're looking at more foundational layers of the cloud and stuff like cryptography libraries, hypervisors. So we're slowly moving from like analyzing specs of what customer sees to analyzing like the software that runs the cloud. So this is really about software code reasoning and not so much policy anymore. So yeah, so Rust is super fast growing. People love that. People love the type safety, the performance, the no garbage collection, like the concurrency, the zero cost abstraction. The package manager is great compared to whatever you have in Java, so people love it. But when you look at it, like a lot of the foundation of Rust is actually rooted in unsafe. Like the standard library has a lot of unsafe, and in some cases, people who are not super experienced at Rust and using lifetimes correctly and that kind of stuff, they would quickly default to using unsafe as an escape hatch. So basically with Kani, we were like, we should build a verification tool that can analyze programs that manipulate raw pointers. So yeah, so just these are like Firecrackers, a hypervisor. S2N is a crypto library. Tokyo is the threaded runtime. Bottle Rocket's something else. All of that uses Rust. And so here comes Kani. So it was started like a few years ago, and the goal was really to give people a way to check very basic properties at scale without having to write a lot of specifications. You just write a basic test harness, and we check automatically for a class of undefined behaviors, like integer overflows or panics. But we also can reason about raw pointers, memory allocations, reallocations, deallocations. And to some extent, we can also reason across language boundary through the CFFI as well. Yeah, so yeah, that's a customer testimony. They discovered bugs. So Kani is mostly a bug finding tool, I would say. It reasons formally about the code. There's work being done right now, has been in progress for like a year and something to make it bounded and actually do real proofs. But today is mostly used as a bounded reasoning engine. So bug finding within the envelope of what your harness specifies as initial state. Yeah, other customer testimonies. So sorry, that's, I think I can skip this one, but that's what we show to developers to tell them that they need symbolic execution even in the most basic of cases. you have a function like this that takes just a 4-tuplet of I64s, there's no way you can text this exhaustively. So if deep inside your function there's a tricky condition that involves like conjunctions, disjunctions, and specific values, you're never going to hit that panic by just fuzzing alone. So even in that case, you testing this exhaustively and knowing if you can actually reach that condition already requires some sort of like more abstract reasoning than just executing the code. So that's the way we're trying to communicate internally to people who just get started with verification, that it's actually, you pretty early hit the need of a reasoning engine. So several times the edge of the universe to test that thing. You can just prove it in a few milliseconds using a symbolic execution engine. So this is what a typical verification harness looks like for Kani. This is non-determinism, so you can just summon a symbolic value that's going to cover the range of the type, and then you can just invoke the function, assert whatever post condition you want, and Kani comes back with a verdict telling you, yeah, what checks were instantiated automatically on your code, and whether they're like the violations are possible or not. And we also do coverage, like reachability analysis. So we for every basic block at the mirror level, we check if it's reachable or not, report any unreachable blocks. So it helps you spot problems with your code. But so that's the typical setup. Most people know how to write that kind of stuff. And it already gets you a lot further than just testing. So yeah, so Kani, it's like implemented as a compiler plugin for Rust C. So we load user crates, we load Kani support crates that gives us models of the Rust C intrinsics, models of the standard library like std-alloc, realloc, that kind of stuff. We compile everything to an intermediate language called Goto, which originated in the CBMC bundle model checker. And the particularity of Goto is that it has a built-in memory model, and it understands allocation, deallocation, pointer aliasing, and it's able to automatically instantiate a number of UB checks. It's going to check that all the raw pointers are used within the lifetimes of the objects they're pointing to. It's going to discover pointer overflows and out-of-bound accesses, that kind of stuff. So what you can do with the built-in properties is check for if panics are reachable in your Rust code, pointer overflow, division by 0. We also have a bit-precise model of floating point. So not super scalable, but useful in some cases. We also check that any signed to unsigned conversion doesn't overflow. And line location or branch coverage, reachability analysis. So that's what you get out of the box. If you want to get further, you can start adding your own inline assertions that you would do in like when you program using assert. And there's ongoing work about extending Kani's support to include function contracts with requires, ensures, and frame conditions, and also loop variants to prove to reason inductively over loops and remove the boundedness limitation. So 2 verdicts, either pass or fail, but there's a third one which is also I don't know, or timeout, or blow up your machine. So one of the cool things with bounded model checking is that usually you're able to produce, in case the property fails, an executable test case that you can load up into the IDE and you can step through with your debugger. So you can use LLDB and you can figure out exactly what's going on in the code. So that arrow is when we inject the test case in your test suite, and you can just save it. So we've done a lot of work to make the installation, deployment of Kani and all the dependencies super easy. So all you have to type is 2 command lines for cargo. So cargo install locked. You can pin everything to specific versions. Cargo Kani setup. and you're good to go. We have a short release cycle every month. Used to be 2 weeks, but now every month we release a new version with bug fixes available for ARM, macOS, x86. So it's very simple to use. And we also have a GitHub action that people can use to trigger Kani regression proofs on their code at every release or every PR even that gets pushed to their code base. Yeah. So what we're trying to sell is the idea of proof-guided development to developers, which is if you're about to write tests, you might just as well write proofs or proof harnesses. So I'm going to guide the presentation with a small example of a resizable byte buffer where part of the storage is inline in the struct and then you transition to the heap. And we use a raw pointer and unsafe for us to handle the heap allocation, just for the sake of the example. So yeah, that's what you call small vec or compact string in Rust. So you start with an inline storage, and when you saturate it, you transition to the heap allocated block, and then when it needs to grow, you're just going to reallocate it to something larger, and you use unsafe for us to do that. And then to index into that vector, you're going to need to do some arithmetic on the index, translate that to a pointer plus some offset, and you want to check that everything is going to remain in bounds. So that's the typical stuff where Kani is going to help you, and it's going to be able to do that verification using just a harness and a bunch of tests, symbolic tests. So yeah, so that would be the style of interface. Good practice, just tell the developers to embed the invariants of the data structure inside of the type itself, so you can use it as just Rust code. So you're going to express the invariant as Rust code. So that's what a proof harness would look like. Just a function allocates a byte buffer, asserts the invariant, holds in the initial state of the buffer. The next one would be actually invoking an arbitrary byte buffer using Kani any, just invoking any value for the resize, and it trigger a resize of the capacity and verify that you land in the invariant again. So this is kind of like manually checking pre-post conditions as you want. To make this work, the Kani any, since there's raw pointers involved, users have to implement their own version of a trait called Kani arbitrary that explains how to synthesize out of thin air a non-atomistic value of that type. So in that case, it would mean allocate the base array, flip a coin to decide if you're going to be in the heap case or the inline storage case. And if so, allocate a non-atomistic blob of bytes, form a non-atomistic value that satisfies the invariant. So it's kind of like we're trying to automatically summon an arbitrary value for the type, but since there's raw pointers and we don't use separation logic to explain what the memory layout looks like, you actually write a program that generates that data. And most people are kind of able to do that naturally. But the only limitation here is that soundness is in your own hands. Because if you generate an arbitrary value that's not the most general possible for your invariant, then you may exercise the code in a overly restricted way. Which is why we're working on contracts as well. But that's the way we would do it. So we're trying to stay away from separation logic and all this stuff and expose all that as Rust code. Yeah, so basically for every method of your interface, you just write the simple harness like this, invoke Kani on the command line. That's where you want to get to initially, or in the end, you want to get to successful verification. What usually happens with unsafe and that kind of analysis is you find a lot of problems. Multiplication overflow, loop unwinding failures, like the Kani detects that you could actually keep unwinding a loop forever because there's some overflow on the counter and you just loop over. And so verification fails. So yeah, a few seconds. And you also find like, panics. You also find UB triggered through unsafe, which is the most interesting about Kani, I guess. So yeah, we handle closures as well. Like we're able to chew on a lot of Rust code. We don't really have abstractions for that. We just compile it down to whatever it means in Mir and then go to, and we execute a very faithful model of the program. We're byte precise. Yeah, no real abstraction, and we just execute forward. Yep.
Oh, sorry. When you're saying that you're byte precise, and you have a faithful communication, so things like intrinsics, how do you work with things like this that's different depending on the law?
So that's empirical, and it's a lot of trial and error. And something we're trying to do right now is, as part of verifying the standard library, which we launched an effort for, is trying to rally people around like specifying intrinsics, giving them a formal pre-post conditions, but basically, yeah, intrinsics you're kind of basically on your own and using test cases to verify that your model seems to be correct. Yeah.
Maybe a similar thing. How do you test that Kani is correct, has the correct semantics of Rust, basically?
So Kani is able to concretely execute test cases as well. So most of the validation we do is basically compared to the semantics that would be given by just executing the code. But most of it is just looking at the code, thinking really hard, and having test cases. So we have a growing set of test cases, but we don't have a formalized semantics of Rust or anything like that. And we regularly get reports of users that say, hey, yeah, this doesn't seem to behave like it should. So short of being like mathematically correct, because we don't have a mathematical spec of Rust, we're just trying to be super reactive when issues like that show up. We investigate, fix, and confirm.
Since it's meant to be like a useful bug fixing tool, it's okay for it to.
Yeah, but as we start getting into unbounded verification, these questions kind of like get more tricky and more pressing. Yeah.
The next presentation so far. So I work with CBMC and Kani in my research. And one question I want to ask is, so here you've been talking about, you've shown a demo of how you would write a proof for a function. But I don't know if it's something that you also do, but let's say you have a bigger software and you need to verify a component in that software. How do you ensure that the proof represents the correct state that gets into that function you're trying to verify?
That's a very good question. So you can decompose proofs. You can have pre-post conditions that are executable. You can embed them in your functions, but the best is to move towards contracts and having pre-post conditions be annotated on your functions. And the approach we take for that is like, once you have a contract, we can check the contract against the function. And for compositional verification, we can take the contract and generate an abstraction of the behavior of the function just based on the contract that kind of omits all the implementation details of that function. And just in the larger verification problem, like poke a hole, replace the function call by the abstraction.
Okay, I assume the later talk this afternoon would cover contract-based verification.
Mm-hmm.
Okay, so then the question I should have asked this in the later talk, but when you then talk about developing contracts, is it the developers that would write the contracts, or is it the verification engineers, and what's the experience of? Because I know in software engineering, usually when developers have to write specifications or contracts, it's always like a pain in the ass, like it's hard. It's prone to errors, they can make mistakes. So I think this will maybe a longer conversation after, but I'm just
Yeah.
If developers have to write the contract, and if they do, what's their experience like, and what maybe we can discuss after.
There's companies where I used to work at where you had developers and you had verifiers. And it was really hard, like, because most of the time the person who writes the code knows why it should be correct and could just write it explicitly. What we find is that tools that are annotation heavy are kind of like not really well liked by the average developer, because making explicit everything that's implicit in their head sometimes seems like extra useless work. And so I think the way we're approaching this is trying to not have not have a very fancy, rich, or complex logic to express specifications, and have something where the specification language is not maybe as powerful as you would need in general, but specifications are executable. So when you write a spec, you can both execute it, you can fuzz your code, generate counterexample, find bugs, but then you can also transition to verification just by writing one spec. And the spec should be as close as possible to executable code. And personally, I think the right way is to ask developers to add invariants to the code, because they're actually designing the thing and they know why it should work. So, yeah.
I wanted to ask, you mentioned that something that you're working on now is bringing in contracts. Is that because you found limitations using the things like asserts and the in-Rust ability to develop and specify?
Yeah, so as soon as you hit a simple loop that iterates more than 25 times, since we just go forward and unwind, like you have to reason inductively to make it scale, so.
This is kind of like to be modular.
Yeah, so we started implementing contracts in CBMC just because we needed to scale proof that where unwinding would not suffice. And so we started with function contracts to abstract like the complicated control flow that would cause the model checker to explode. So for us, contract is not, we came to it from the performance perspective in trying to scale proofs, and other people see contracts as a language should have contracts, and you should do contract-based design, and contract should be everywhere and should completely formalize the behavior of your code.
You're like as required.
Yeah, for us it's more like sometimes a function just does what it does. Don't force me to explain that to you in logic again. Here's the code, it's simple enough, you can symbolically execute it. So yeah, coming to contracts from a performance and scalability perspective.
Very interesting talk. About this contract versus concrete execution stuff. Usually when you write a contract, you work at a level of abstraction that not only abstracts the control flow of the program, but also maybe abstracts the data and so on. How does that, if I write a contract or something, how does that interplay with your byte level precise execution? Do I write my contract at that level of precision?
Yeah, so our contracts, for instance, we have we don't even use quantifiers yet. It's very basic stuff. We're trying to express the contract that's just the weakest contract possible that would allow us to prove memory safety.
Are you going to have examples of these contracts later in the talk?
Yes, coming second session about this. But for an example, like we do frame condition tracking when we do modular verification. The ghost code that tracks the frame is itself expressed as a set of bit vectors, and so we're sticking with that bit precise kind of stuff. So we model also the ghost code is also byte precise code, and we check for UB in that code as well. All right, resuming. So yeah, so that just an example of what this looks like. So even this is already too much for certain people. So people want to compute, they want to resize the vector. So like, okay, I'm just going to do a power of 2 progression. So they write this, but then you write, okay, so now tell me what's the power of 2. So that's the power of 2, and tell me what's the smallest power of 2 possible. And that should be that function. So for some people, it's already kind of too much. So that's the minimum amount of work we can ask for them to do. And then you just write this thing. So LLMs are coming to the rescue here. You can use LLM to write a lot of that stuff. Like if it's simple enough, the LLM is going to do a good job at translating your natural language prompt into a spec function in Rust and a proof harness that looks like a test harness. So I think we're betting on that too. Yeah. No, the spec would be natural language, and
In the, but the natural language.
yeah.
This is formal, and then how do you check that the two are related at all?
That code is executable, so you can run it. You can run your spec. You can execute it. You can test it as well if you want. But yeah, so I mean, there's a human in the loop. Like someone is going to look at the code and make sure it's correct.
I'm just reflecting on a comment you made earlier in the talk about how one has to carefully think about these things to make sure that you're adequately modeling the execution environment of the program. And if you have an AI generating it, then
So the thing is, you either write the code or the spec, and then if they diverge, then one of them is wrong. So you should not use LLMs to write all of your code, the spec and the code. But
they don't diverge,
yeah.
then you may have undertested the program.
Yeah, sure. But we're assuming we're in a supervised context where the human looks at what's going on. Yeah, but I agree. Like that's a failure mode. Like they can both be wrong and agree. Yeah. Right. So we have this VS Code extension where you can basically run the proofs from the VS Code extension. You can get a report of what assertion failed. Then you can click on you can click here and it's going to embed the test case inside of your code. And then you can, this test case here, the byte vector here, is just going to contain all the non-deterministic Oracle variables that we use, like when we do Kani any. All of these gets just serialized as a huge bag of bytes, and then when you run the test case through that harness, all the Kani any gets populated from that byte vector. So we can replay counterexample that invoke non-determinism like this. And you can step through the debugger and you can realize, oh, I forgot to do an upper bound check, so my counter can overflow and my loop can loop forever because yeah. So by being able to execute counterexamples, we also find problems where our counterexample is spurious and we can fix that. So being able to execute the evidence is kind of cool. So that was a slide to show you how stupid symbolic execution can be. So if you have a simple loop, we just go through that loop and generate this huge formula that captures path conditions, branch conditions, and at every step of the loop, we just instantiate the verification conditions. But what really CBMC does is like unfold this giant formula. So we end up with huge SMT or SAT instances that we just solve, and we're trying to be incremental doing all of this, so it's still relatively performant, but it's pretty stupid. So if you go like more than a few iterations, you're going to need inductive reasoning. But it's surprising how far we can get just doing that. All right. Yeah, so ultimately the goal is to converge to that situation where the function works, and then you're like, oh, I'm going to ask my favorite LLM to optimize that code for me, and it's going to come up with a bunch of like dirty byte level tricks to compute powers of 2 decomposition or whatever. Since we're a bit precise model checker, we can verify that this new version of the code that uses bit shifts and ORs and stuff also works. By keeping the specification the same and just optimizing this thing locally. So yeah, so that was the first attempt at this container, and after working on it with Kani, you have raw pointers, you have a bunch of reallocs, and then you were basically forced by the model checker to add all the error handling and all that stuff. So that's the net benefit. And after like, I don't know, like an hour of work, you get to a verified version of it. So yeah, the takeaways and the message we're trying to promote is proof harnesses are very similar to traditional test harnesses, but the return on investment is a lot higher. And we have an integration with something called Bolero. It's a library that just does fuzzing. And it has a framework for generators that generate random values. We work with Bolero to make Kani a backend engine for Bolero. So you can write the Bolero test harness that does fuzzing, and then when you're ready to flick the switch, you can go to symbolic execution. and you can smoothly transition from just fuzz testing to basic proof-based, like harness-based proofs, and then you can start going further, adding invariants, post conditions, that sort of stuff. So we're trying to make it effortless. And then at some point, people are going to get frustrated by the limitations of the tool, but they're going to be like, now I like verification, and then they can move on to different tools like Crusoe, INES, other tools that can do much more, but require like more investment as well, understanding the logic and the specification language and all that stuff. So we're trying to get a gateway drug to more like fully formal verification. So scaling automated reasoning obviously requires decomposition, but that's where things get hairy and tricky for users. So we're slowly getting there, but we're still mostly a bounded model checking engine. The tool has limitations that we're continuously addressing. And we're not really analyzing all the Rust UB classes for now. The most recent thing we've been trying to do is to extend our UB checks for pointers to the stack borrow, proof obligations type of stuff, where you basically track the lifetimes, like by associating a stack that like the presence in the stack of the back reference defines the lifetime, and then we check the proper ordering of a pointer and the reference accesses. So we're still working on that, so we're far from being able to cover everything. Okay, so Kani, actively developed and supported. It's growing, and we've been accepting more and more outside contributions. And it's really long-term commitment. We have a full team working on this, and we have a lot of internal projects. It's easy to onboard. We're really focusing on the ease of use. Coming soon, compositional reasoning by Ziad. Also, like more classes of UB that we're checking for. So if you start using Kani and you start relying on it, you can be sure it's going to be around for a while, because we're actively maintaining it. And these are resources that you can consult. In particular, so this one, so these are blog posts, examples of use and that kind of stuff, but this is the most recent project. It's our fork of the Rust Standard Library, where we're inviting people to participate and contribute in solving challenges. So Kani is the main tool that we started this with. Now we have very fast. We have KMIR. We have a fork of CBMC as well that can analyze MIR code. And we're inviting everyone with tools to apply and submit a tool, and then so that the tool can be used to solve the verification challenges. So we're at the stage where we're trying to apply to run Kani on as many functions of the standard library as possible. And I think we had a recent breakthrough. We were able to run Kani on over 4,000 functions of the standard library and discover a bunch of issues that we're still diagnosing. So I'm really encouraging everyone with a verification tool to submit and come solve the problems with us.